contact in water, it goes to hydronium ion and conjugate base. Here water is acting as a base because it could accept a proton from the acid. So the terminologies are, if you have acid 1, base 1, you would have conjugate acid 1 and conjugate base 1. The equilibrium constant for most weak acids is low number because the dissociation is not complete, therefore it is a very low number. This is a product of the hydronium ion times the conjugate base over the unassociated acid. The acid dissociation constant can be also rewritten as a pKa value, that means a minus log of Ka, which is pKa equals pH plus the log of conjugate base A minus, this conjugate base, over the acid. So this indicates that the larger the Ka means, most of it is dissociated in this form. The larger the Ka is, the more acidic, and the larger the pKa means, the less acidic. So it's an inverse relationship. Even though they are measuring the same acidic strengths, they are in a reverse. One is a minus log of Ka, and the other is just the dissociation constant. So weak acids generally dissociate very poorly into their conjugate acid and conjugate base, and they are defined by this equilibrium constant, and also we can measure that equilibrium constant as pKa, pH log of conjugate base over the acid. Similarly, we can write also a similar equation for polyprotic acids. That means if you have more than one proton that can be dissociated, you would have associated dissociation constants. For example, if you have H2A, that means a diprotic acid, there would be a stepwise dissociation of the protons to completely its conjugate bases. So we'll see what the dissociation constants look for a diprotic acid. Diprotic acid in contact with water, that's the aqueous solution of a weak acid, which is diprotic. It would dissociate into its conjugate base. In this time, there was one more proton here, and one of the proton would be abstracted by water. So you have a hydronium ion and the conjugate base. So relevant to this first equilibrium, you have the acid dissociation constant Ka1, which is the H3O, that is the hydronium ion concentration, times the conjugate base Ha minus over the acid. In the stepwise dissociation of the conjugate base, again, one more proton to release. This now serves as a conjugate acid in this context. The conjugate acid donates one of its proton and forms the conjugate acid, and completely deprotonated or completely free of a proton, that's the conjugate base. So relevant to this is a dissociation constant 2, which equals the hydronium ion concentration times its conjugate base over the acid. So this is a diprotic acid and its dissociation constant. So the associated pKa1, pKa2 are similar to what we have seen for the monoprotic acid. Here we have another important constant, which is the product of water constant, which is Ka times Kb. Ka is the acid dissociation constant, Kb is the base constant, and it's about 10 to the minus 14. How is this concept derived, or how do we get that constant? Let's do an example of take a weak acid called acetic acid. Acetic acid is a weak acid with one proton. In aqueous medium, it would donate its proton, and the acetate conjugate and the hydronium ion are products. But as I already said, this is a very weak acid. The equilibrium shifts to the right very slowly or very low. Therefore, the acid dissociation constant would be the product of the acetate conjugate base and the hydronium ion over the concentration of the acetic acid. So this is Ka, the acid dissociation constant, which we have already introduced before. Where does the Kb comes from? That is a base constant. For a given acid, there is a conjugate base. So if we just consider the conjugate base and it's in aqueous medium, there is an equilibrium that is also the reverse of that. That is the acetate ion, an ion actually, deprotonates one of the proton and becomes the acetic acid and releases 1 mole of the hydroxide ion. Still, this can be expressed as a base constant, Kb. That Kb is equal to the acetic acid times the hydroxide ion over the acetate conjugate base. So we have Ka and Kb for the same weak acid in water. So we should be able to write both the acid form, acid dissociation, or the base using the conjugate base. So this, if you are familiar how to write these two equations and write Ka and Kb, if you just take the product of Ka and Kb, that means if you just take Ka, this whole formula, and if you take the whole formula, Ka and Kb, the product of the two is actually constant, which gives you the hydronium ion concentration times the OH minus, which we have already previously introduced to be constant, 1 times 10 to the minus 14, which is K of water. What happens is the acetate conjugate base cancels out with the acetate conjugate base, and the acetic acid cancels out with the acetic acid. So the only factors that are remaining would be the hydronium ion concentration and the hydroxide ion. Therefore, the product would be just the hydronium ion concentration times the OH minus. So we will apply this concept when we are doing real calculations in the future. For now, you only need to know Ka times Kb is constant to be 1 times 10 minus 14. Okay, so far we have introduced several equations and concepts, and I would like to demonstrate those equations and concepts by solving a few problems. Problem 1 says, what is the pH of a monoprotic weak acid with acid dissociation constant of 1.75 10 to the minus 5 and 0.1 molar concentration? So this is just an acid, a weak acid with a very low dissociation constant. That means a very weak acid to the minus 5. We just need to just set up an equation where the formula would be, it's a monoprotic, it has only 1 proton. And in aqueous medium, this is the dissociation equilibrium that you can find. So you have hydronium ion and the conjugate base. So it's a monoprotic acid. It would have only 1 dissociation constant, Ka. It's the concentration of hydronium ion times the conjugate base and divided by the equilibrium concentration of the weak acid itself. Usually in most practical experiences, this is how you set up your equation. First, the acid would equilibrate between hydronium and the conjugate base. Initially, let's assume it's 0.1 molar. That's just the initial concentration. So assuming that initially we have 0 of the hydronium and 0 concentration of the conjugate base. But at equilibrium, some of it would dissociate. That means X amount would dissociate to form the hydronium and the conjugate base in equal amount, X and X, because this is 1 mole of a monoprotic acid. You would have equal amount of hydronium and conjugate base. But if you just apply 0.1 minus X in your equation here, it might be a little complicated, and it will lead to you, so you need to solve a quadratic equation. To just avoid that and give a very reasonable assumption would be, since the acid is dissociating into a very low extent, that X is, as compared to the 0.1 molar, it's very low. Therefore, 0.1 minus X, the difference might not be significant if you just leave out that and you approximate it to 0.1. And you have X amount that's produced and X amount that's produced. Now, if you just use this equation, Ka, which is 1.75 times 10 to the minus 5 equals X squared, that is X times X over 0.1. Therefore, X would be 0.1 times 0.75 under the square root. That X would be one of the hydronium ion concentration, which is 1.32 times 10 to the minus 3 molar. Sorry, there should be a molar there, molar sign. Therefore, now we have to convert this hydronium ion concentration to a pH. pH, we know that. pH equals minus log of the concentration of hydronium ion minus log of 1.32 times 10 to the minus 3. Therefore, pH becomes 2.88. So this is how you would solve in weak acid dissociation, and if the dissociation constant is given. So any of this value can be calculated using this general strategy. Now, we'll be solving other problems, and we'll continue problem 2. Doing some problems in acid base. A weak acid, a pH of a weak acid would be calculated. For example, for this problem, number 2, what is the pH of a 0.1 molar solution of a diprotic acid with Ka1 of 6.2 times 10 to the minus 5, and the second ionization constant is 2.3 times 10 to the minus 6. So basically, the first equation, the first equilibrium equation would be the diprotic acid in aqueous solution would give us the first proton and the conjugate base. So that's what we're going to use for calculating the pH of that solution. So from Ka1, that means acid dissociation constant 1, we have hydronium ion concentration in equilibrium, and also the conjugate base from that acid over the concentration of the undissociated acid. Remember, we are always assuming that to its initial concentration of 0.1, because this acid dissociates in a very low extent. It's not a very strong acid. So whatever we have at initial would be still can be approximated to the initial concentration of the acid, but that's not the reality. So now I would just set up the equation where this would dissociate into equal for each 1 mole of hydronium and 1 mole of the conjugate base is dissociated. So they are in equal proportion and they are equal concentration. So if this is X, that would be X. So X squared over 0.1 would be the acid dissociation constant. Then to solve for x, you have to multiply 0.1 times that and take the square root of that product. Plugging it into the pH equals the minus log of the hydronium ion concentration. If you just plug that number into this, you'd get a pH of 2.6. So this initial solution of a diprotic acid has a pH of 2.6. So this is just the acid, not in a titration, no base was added, just the pH of this solution at a 0.1 molar solution has a pH of 2.6. So you just need to calculate from the acid dissociation constant what the pH is. So it's a very simple calculation to get for the pH of the solution. Solve our problems. Number 3 asks for what are the respective pH values of a 0.0 molar acid with Ka value of 1.85 10 to the minus 5 at 25%, 50%, 75% dissociated. This question is a little bit challenging, but in a way that it would show you that the monoprotic acid is dissociating at different levels. That means it's dissociated, or the conjugate base is being formed at 25% of it, 50% of it, 75% of it dissociates into the to the right. So to solve this problem, first of all, we have this equation, which we have covered earlier. pH is equal to pKa plus the logarithm of the conjugate base over the undissociated acid. So that's the fraction of basically the ratio of the dissociated conjugate base over the undissociated one. So here in the question, it's asking you if 25% of the acid is converted to this form, or 50% of it is formed. So progressively, it is dissociated more to the right. So as later we calculate and see what that solution in terms of its pH value would be. So applying the pH equals pKa plus the logarithm of A minus 2HA HA is equal to pH equals. So if you just do the pKa of this, convert this into the minus log of Ka, that is the negative log of 1.85 10 to the minus 5, would give you 4.74. So plugging into that equation would be pH equals 4.74 plus log of the different ratios of the conjugate base to the acid. Now, solving for a 25% dissociation, pH equals 4.74 plus the logarithm of 0.25 of HA. Now I'm just substituting the A minus value with 25% of HA, and the 75% HA remains in the solution. That means your initial is 75 is remaining, but 25% has gone to this form. So that's therefore you are just simplifying the equation so that now you have only the numerical values of 0.25 to 0.75. You'll cancel this. 0.25 to 0.75 is 0.333. That means the logarithm of 0.333 would be 0.48 minus 0.48. Of course, it's less than 1. So the pH would be 4.74 minus 0.48. Now the pH is 4.26. How about if 50% of this is converted into this form? That means if 50% of the acid is dissociated into its hydronium and the conjugate base, the formula for that would be at 50% pH equals 4.74 plus the log of 50% of that is 0.5A times the concentration of HA, and the remaining one of course would be its 50%, it's 0.5 times HA. Therefore, it's a very simplified equation where you just cancel that. 0.5 to 0.5 is 1. At that point, when the 50% of this is dissociated to this, that means log 1. Log 1 is 0, therefore pH equals pKa actually. So as this 50% dissociation, pH and pKa would become equal. So remember that. For a weak acid, at 50% of dissociation, pH and pKa are the same. So 4.74, 4.74. As you see, as more of this is dissociated into the right, the equilibrium shifted to making more of the conjugate base, the pH now increases. So it's becoming more and more basic. So let's say at 75%, it's almost 75% of it is in this form, but 25% remaining in solution. So pH equals 4.74 plus the logarithm of 0.75 of HA for this value, and the remaining 0.25 of HA. Now you cancel this. 0.75 to 0.25 is 3. Logarithm of 3 is 0.48. So now pH equals pKa 4.74 plus 0.48, which is 5.22. Now this shows you that as the equilibrium is shifted more to this solution, or to the conjugate base and the conjugate acid, the pH increases. So pH goes from 4.26, 5.22. So this all shows you how pH depends on the degree of dissociation of your weak acid. Continuing our discussion on titration, specifically with the strong acid and the strong base. The titration of a strong acid and strong base are quite different from a titration of a weak acid with strong base or a strong base with a weak acid. The reason being, in a strong acid, strong base titration, you have a strong acid such as hydrochloric acid and a strong base sodium hydroxide. There is no any equilibrium. Most of it is completely in a fast reaction, converts to sodium chloride and water. The main reactions are the proton from the acid and the hydroxide ion forming water. So most of the neutralization reactions produce a salt and water. Therefore, a strong acid, a strong base titration gives you a very simple diagram of a change of pH as you are adding sodium hydroxide. So titration is usually used to determine, for example, if you have a very well standardized base, for example, if you have a 0.1 molar sodium hydroxide, you can titrate it against a known fixed amount of volume, but the concentration might not be known. From the graph, you could be able to determine what its concentrations are. But here as an example, I will show you a known amount or a concentration of hydrochloric acid, and 0.1 molar sodium hydroxide is used in a titration. So in the titration of 0.1 molar hydrochloric acid, initially, the curve is you have a pH axis in Y from 0 to 14, and in the x-axis you have a sequential addition of sodium hydroxide, which is 0.1 molar sodium hydroxide. Here you see a 5, 10, 15 ml added stepwise. As you are adding your sodium hydroxide to the initial hydrochloric acid in a flask, your pH slowly rise up, and around near to the equivalence point, the pH suddenly starts to jump. So there is a sharp increase in the pH. So In a weak acid, strong base titration, mostly this curve is not well defined. Sometimes it is, at least for the first ionization of a monoprotic acid. But the titration curve for a strong acid, a strong base, is a well-defined curve, and each point can be calculated. For example, now, as I already told you, let's have a flask, an aromatic flask, 25 ml, and a 0.1 molar hydrochloric acid. So at no addition of a base, at 0 point, without adding any base, what is the pH of that solution? Since it's a strong acid, and a strong acid dissociates completely to a hydronium ion and a chloride conjugate base. So this is your acid, your base, conjugate acid, conjugate base. This terminology still applies, but the dissociation is 100%. Therefore, in solution, if you have initial solution of 0.1 molar hydrochloric acid in water or in aqueous solution, you would have also a hydronium ion concentration of 0.1 molar. So that is what you have at the initial stage of adding no sodium hydroxide. So 0.1 molar HCl produces 0.1 molar hydronium ion and 0.1 molar of the conjugate base. We know pH is a minus log of the concentration of hydronium ion. Therefore, pH is 1. So at this point right here in the pH curve is pH 1. We start at pH 1. You see, and now we start titrating. Titrating means you are adding a controlled amount of sodium hydroxide to your acid solution to neutralize stepwise the proton. So here is a reaction, a neutralization reaction, of course, because you are producing a neutral sodium chloride in water. So as you are adding your sodium hydroxide to the HCl in your flask, the pH slowly starts to rise until where it reaches to an equivalence point. What's an equivalence point? Now, the second important concept to define will be equivalence point. At the equivalence point, it means the number of moles of a base. The number of moles of a base equals the number of moles of the acid. In your solution, you have an equal number of moles of base and an equal number of moles of the acid. That means a matching amount of sodium hydroxide is added to the hydrochloric acid. At that point, your pH is 7, because from a K of water, we know that is hydronium ion times hydroxide is 110 to the minus 14. pH plus pOH is 14. Therefore, pH would be just a concentration of the hydronium ion, which equals to the concentration of hydroxide ion. Therefore, pH is 7. So what does that mean in terms of number of moles? So now here for example, equal number of moles of sodium hydroxide with HCl would be reached when you are adding 25 ml of 0.1 molar sodium hydroxide. Even though I didn't mention here, if you see, if you just multiply 25 ml times 0.1, you'll have 2.5 millimoles. That should exactly equal to 25 times 0.1 hydrochloric acid, which is 2.5 millimole. So at that point, when you add exactly 25 ml of sodium hydroxide to this solution, the number of moles or millimoles are equal. At that point, the number of moles of base and number of moles of the acid are equal. That gives you a neutral pH, pH 7. How about when you are just not adding 25, but just only 15 ml? The pH says it's 1.6. I'll show you with a demonstration of a calculation how 1.6 is obtained. So here, after adding 15 ml, what it means is you have added how many millimoles? 15 ml times 0.1 molar would give you 1.5 millimole. So if you have 1.5 millimole of sodium hydroxide added, that means you have neutralized 1.5 millimole of the hydrochloric acid. The remaining in solution would be from 2.5 millimole. If you just subtract 1.5 millimole, you are just left with 1 millimole. So 1 millimole of hydronium ion or hydrochloric acid is left because you have added 15 ml times 0.1, that's 1.5 millimole. 1.5 millimole would neutralize 1.5 millimole of the hydrochloric acid. But what you have initially is 2.5 millimole. Therefore, you are left with 1 millimole. So 1 millimole of hydrochloric acid gives you 1 millimole of hydronium ion. What's 1 millimole? Now, the volume is now changed. So remember, I have 1 millimole left, but the volume is I have 25 and 15. So 25 plus 15, it is 40 ml. So 1 millimole over 40 ml it gives you a concentration of the hydronium ion. That pH would be minus log of that concentration. So it would get pH equals 1.6. So remember how we got this. We have 15 millimole, 15 times 0.1 molar, that's 1.5 millimole. Once I added 1.5 millimole, I am subtracting that much hydrochloric acid, that much has reacted or neutralized. From 2.5 millimole, I am subtracting 1.5 millimole, that leaves me just 1 millimole. At this point, I have only 1 millimole of the hydrochloric acid or H+. That means 1 millimole divided by the volume to get the concentration. That would be, I have 25, and to the 25 ml, we have added 15. The volume is 40 ml. So divide 1 millimole by 40 ml. That would give you the concentration of hydrogen, whose pH calculated by this formula would give me 1.6. Another concept would be, once you reach added equal amount of moles of 25 by 0.1 molar and 25 ml by 0.1 molar hydrochloric acid, that is the equivalence point. What happens beyond the equivalence point? For example, what is the pH after 30 ml is added? Now remember, the solution is now more basic because all of the hydrochloric acid is consumed because you have added enough sodium hydroxide to neutralize this reaction. 25 ml of 0.1 neutralizes all of this. Therefore, now what I'm left with in the solution is a basic sodium hydroxide. I'm just adding 5 ml more, which is 30 ml. The pH is 11.96. How do we get the 11.96? Basically, what is the excess amount I added? From the neutral point, the total I have is 25 times 0.1, which is 2.5 millimole, but I added 30 ml, which I have is 3 millimole. I have added 3 millimole of sodium hydroxide already, but what I have a maximum is 2.5 millimole. 3 millimole minus 2.5 millimole is 0.5 millimole excess sodium hydroxide is in the solution. So I have 0.5 millimole excess sodium hydroxide. What is 0.5 millimole in concentration? Since I had now I need to get the volume. I have 25, but I added 30, that is 55 millimole, or 55 ml. So I would divide 0.5 by 55 to get the concentration. That concentration is not a hydronium ion concentration. That concentration is a hydroxide concentration. Once you calculate that hydroxide concentration, pOH of that concentration would give you the pOH value of the sodium hydroxide. But we know that if we get pOH, the pH is 14 minus the pOH. That's how we got 11.96 pH. So this is how the curve is constructed. Mostly a strong acid, a strong base titration curve is very simple, but we will continue our discussion on the titration of, for example, a strong acid with a weak base or a weak acid with a strong base in our next discussion. Continuing our discussion on titration still, just to give you an example of how you apply a titration equation or a titration curve to solve a problem. Here we are trying to titrate an unknown concentration of hydrochloric acid with a known concentration of sodium hydroxide, which is a neutralization reaction to give you water. So the main reactants are obviously the hydronium ion with a combination to the hydroxide ion to make water. So a titration reaction is actually a neutralization reaction. So in this problem, it's asking what is the concentration of a 10.5 ml of hydrochloric acid. You don't know what its concentration is. One of the application of titration is to know a concentration of an unknown acid or a base, which is completely titrated with 20 ml of 0.075 molar sodium hydroxide. So the experimental setup is that you have a pH versus volume of sodium hydroxide added. That means you want to know at what point is the biggest change in the curve. So from the curve, you can just see how much was added because it has already told you. Maybe you don't even need to see the curve here, right here, but 20 ml of 0.075 molar sodium hydroxide is completely titrates out your unknown acid. So what is the concentration of your hydrochloric acid? We know at the equivalence point where you have added 20 ml of that concentration was sufficient to match up the hydrochloric acid. Since hydrochloric acid is a monoprotic acid, it has only one proton, and the relationship stoichiometrically is 1:1. 1 mole needs 1 mole reaction. So at the equivalence point also, it's true that the moles of sodium hydroxide is equal to the moles of hydrochloric acid. What is the moles of sodium hydroxide that was used? It is just 20 ml of sodium hydroxide times its concentration, which is 0.075 molar sodium hydroxide. That would give you the millimoles or moles of hydrochloric acid. So 20 times 0.075 is 1.5 millimole. That means at the equivalence point, where you have added 1.5 millimoles of sodium hydroxide, it should match to the millimoles of hydrochloric acid. That's your equivalence point. Therefore, the concentration of hydrochloric acid would be 1.5 millimole divided by the volume. So since you are just asked what is the concentration of your initial hydrochloric acid, you don't have to combine this volume. Just that number of millimoles divided by its initial volume of hydrochloric acid would give you 0.15 molar. So a 0.15 molar hydrochloric acid of 10.5 ml would match or equals in the number of moles by 20 ml of 0.075 molar sodium hydroxide. So the concentration, the unknown acid, is now directly determined from the titration curve or from the information that was given here. So for example, if the volume was not given and only the concentration of 0.075 molar sodium hydroxide was given, you can also come and see in the curve, oh, it took 20 ml to get to the equivalence point. So there is no need actually in the question to give you this information, because that you can also read that volume from the titration curve. Titration curve shows you have consumed 20 ml of 0.075 molar to come to the equivalence point. So the concentration then would be that millimoles divided by its volume, what the volume was given for hydrochloric acid, which gives you 0.15 molar. Okay, let's continue our discussion on the titration of a weak diprotic acid with a strong base, such as sodium hydroxide. There are equilibrium constants that are necessary to do these calculations. Acid dissociation constant of your weak acid is a multi-step process where you have two equilibriums, that is Ka1 and Ka2, represented by Ka1 and Ka2. For the first proton, this is a dissociation where hydronium ion and conjugate base over concentration of the acid. Ka2 would be the second conjugate or the amphoteric acid releasing its last proton. So you have this equilibrium represented as Ka1, Ka2. Importantly, we also remember this in any of the equilibrium constants. pH actually corresponds to the pKa plus log of the conjugate acid to the conjugate base to the acid. So fundamentally, for the two protons, you have associated equilibrium constants, and also the pH is defined by such equation. So the titration of a weak diprotic acid with a strong base is a little much different than titrating with strong acid with a strong base. Therefore, we have to pay attention in terms of what are the main important points in calculating this pH in the weak acid case. Initially, for example, the experiment is done where you have an unknown amount of weak acid in a flask, and you are titrating by adding a volume of sodium hydroxide, known concentration of sodium hydroxide, and that would be a titration curve. So pH is in the y-axis, and x would be the volume of the base that's being added. Initially, the weak acid has its own pH. That can be easily calculated from, for example, from a Ka value. So Ka value would be hydronium ion concentration, conjugate base, and the weak acid. So this can be just calculated at time 0. That means by approximating the concentration of the acid to be the initial concentration of the weak acid. For example, if I know the concentration of a 0.1 molar weak acid, I can calculate this pH based on using this equation. So this and that would be equal. That would give me x squared. And since I know the initial concentration, such as 0.1, for example, and if this number is known, usually the acid dissociation constants are in a table, then you can calculate the pH at that point. But from now here on, these are experimentally determined points. That means the pH are measured as you are adding your sodium hydroxide. For example, as you are adding more and more of the base to the weak acid, there is a pH change, which is described by this curve. Here you see 2 points. Here is end point 1 and end point 2. That means it's just a neutralization of the first proton requires that much volume of sodium hydroxide and certain concentration. That gives you the first mole of sodium hydroxide that is neutralizing the first proton. Endpoint 2 is characterized by the complete deprotonation or neutralization using the addition of a base to this. You have a basic solution of that to convert it into completely the conjugate base. This is the autoprotolysis. This is just the equilibrium that exists with the acid without any base. But as you are adding base, you are removing this. You are removing the hydronium ion ions. Therefore, as you just remove the hydronium ion from the solution or neutralize it, the pH starts to increase. But where at a point, for example, endpoint 1, you have added sufficient or exactly the same number of moles of the weak acid for a single proton base that was added to completely neutralize the first proton and the second proton. How do you calculate the pH? By calculation. At this point, for example, experimentally, you can determine what that pH is. But luckily, you have also a way to calculate the pH. If you just take pKa1, pKa2, and divide it by 2, that pH would be endpoint 1 for a diprotic acid. How do you calculate pKa1, for example? pKa1 is calculated, that is from pH 1, whatever pH you have, and the pKa1 would be equal at a point where the conjugate base, meaning this, is equal to the concentration of the acid. So in the equilibrium solution, if the conjugate acid or the conjugate base, in this case, is a base, are equal, this ratio will become 1. So pH and pK, the pH that you measured as you are adding sodium hydroxide, at this point, this is halfway. That means if it is 50% of that and this is 50% remaining, that would be 1. So at halfway, before the end point, your pH and pKa1 are equal because this 0.5 of this and 0.5 of that would be equal. Therefore, pH1, pH that's being measured, is the same as pKa1. Also here at pKa2, pKa2 is calculated from minus log of Ka2, and you have a pH that you are determining. In pKa2 would be, if you write pH2, for example, would be pKa2 and the concentration of the conjugate base and the HA are equal. At that point, when these two are equal, pH that's being measured equals to pKa2. So if you just know minus log, if you just have a Ka2 value from a table, if you take minus log of Ka2, that corresponds halfway between the endpoint 1 and endpoint 2. So this is also halfway, which is called pKa2. That's minus log of Ka2. So if you just have this pKa2, the endpoint would be exactly the amount of volume that was added from endpoint 1 to pKa2, and next one would be that much volume would be added to reach to endpoint 2. That means for a diprotic acid, you have 2 protons. So the first proton would be deprotonated, and you need equal amount from here to here, whatever volume you took, you need also that much volume of sodium hydroxide or your base to completely reach to endpoint 2. Therefore, halfway would be pKa2. That means the conjugate base concentration and the conjugate acid concentration, when they are equal, pKa2 would be equal to that pH. So once you reach endpoint 2, the calculation of the pH, for example, for this point is a little different. Here you need to consider the base constant of your conjugate base. That could be equated as similar, analogous to Ka1, or acid dissociation constant. The base constant would be the product of these two over the concentration of the conjugate base. In this case, the base. So Kb actually would be, since this would produce equal amount of OH minus and H minus, since we are interested in the POH, once we reach past the end point of point 2, most of it is very basic. That would be excess hydroxide. So we are concerned in finding the concentration of hydroxide ion. So here I would just say hydroxide ion concentration square over the conjugate base equals Kb. So we need to apply this or find the POH to find the pH at endpoint 2. It can be measured by your pH, but it can be also calculated using this formula.
Hi everyone, here is a setup for today's experiment. Today's experiment involves titration. Titration is a simple chemical analysis where you need a burette, an Erlenmeyer flask, and also a pH meter. In this experiment, we are going to titrate a triprotic acid against a 0.1 molar sodium hydroxide. As we are adding each 1 ml of sodium hydroxide from the burette, a pH changes. We record that pH. In most cases, obviously, it goes from low acidic pH to a higher pH. At each equivalence point, there is a significant change in pH. So as we are adding the sodium hydroxide, each proton would be neutralized stepwise at a point where endpoint 1 would show the neutralization of proton 1, 2, and 3 respectively. So after collecting each pH value against the volume of sodium hydroxide added, we're gonna plot a graph which has a pH versus volume of sodium hydroxide added.
Forward, this is an electrode, pH electrode, and just measure the initial acidic pH. Obviously that's very acidic. I'll just say pH. It's right now it's showing about 1.71. So I'll wait until it stabilizes. So that's the initial acidic solution for our titration. It is 25 ml and it's a triprotic acid. So the initial pH will be measured. Once we have the initial pH measured, we will titrate it against 0.1 molar sodium hydroxide. So the pH is about now stabilizing at 1.6. Now slowly the pH is going up to now 2.09. We are added about 10 ml of sodium hydroxide. At this point the pH is 2.09. At 30 ml we are at 2.82 pH. That's 30 ml of sodium hydroxide added, and the pH is 2.82. I will continue adding. So I added 1 ml more. Now the pH has jumped to 2.93. It looks like it's some of the equivalence point, I believe. This is 3.11. It's the highest change I saw so far. This also looks like a rapid change. At 34 ml of sodium hydroxide, we see a pH of 3.92. So it's slowly going up. This looks like the highest jump. It should be an equivalence point, because from 3.92 we are jumping to about 5.35. So it definitely shows a point where there is a proton exchange. That means there is an equivalence point of sodium hydroxide has been used. So now the titration is progressing well, and I have added already 44 ml of sodium hydroxide, and the pH is 6.75. Now we are going slowly to the basic region of the titration curve, because we are more than pH 7, which is 7.58 at 54 ml of sodium hydroxide. So we are in the basic region of the titration curve. You can see here now the biggest jump, since the earlier one was 8.43. After addition of the last 1 ml, we have jumped to 9.74. It's almost flat now because it has reached where most of the protons are deprotonated, and we might be well past the third proton has been already deprotonated. Almost the curve has plateaued, and the pH is changing very slowly. That means it's reached the plateau of the curve. Now it's 11.43. I'll keep on adding some more volume, where the point that K of water is being used for the calculation, because most of your solution now is purely a basic solution, where the equilibrium is mostly hydroxide ion is mostly in the solution. Therefore the application in the calculation would involve the K of the acid and K of the base, and also the K of water to calculate all of the equilibrium concentrations you need to know. So at 70 ml, the final pH is 11.56. So that's the end of our titration. Next step is to plot the pH against the volume of sodium hydroxide added, and from the curve we're going to analyze the pKa1, pKa2, pKa3, and also equivalence point 1, equivalence point 2, and equivalence point 3.